Hello, and thank you for being here. The talk is called Dissecting the RabbitMQ Internal Architecture. My name is Alvaro Videla, and you don't need to pronounce it, basically. And a bit about me, I work at RabbitMQ. We are right now 4 people working at Rabbit. I am co-author of the book RabbitMQ in Action. I made a simulator I will show you later what it's useful for. Don't know here who knows Erlang? Everybody, okay. So basically I can skip my talk and go home. Or some can come here and give it. So I brought some stuff about the internals of Rabbit there. I should write more maybe. And that's my contact info. That's the book that I know it can be acquired in Russian websites, sorry, or you can buy it somewhere. Depends on you. As long as you read it, I don't care how you got it. Don't let me talk about that. One of the first copies that went out into the Russian market was actually from a functional programmer from Australia. So I don't know what this guy was doing, but he leaked some states. He has some side effects when he bought the book. So, because it has the name below, like this copy belongs to whoever. So if you want to work at Rabbit, get in touch later, and that's the description of the job, basically. And now that we are a LambdaCon, you should use this programming language. It's much better than whatever you ever heard about. It's a better closure. So, starting with the talk. Intro. The idea is to show you or tell you what Rabbit is doing so we understand what problem Rabbit is trying to solve, because just to talk about the internals without really knowing what problem we are going after, it's quite hard. Then we go into some part of the internals. We may see, if we have time, what happened inside a message and inside the Rabbit message store. And then I want to talk about behaviors and extensibility from the RabbitMQ point of view. So what is RabbitMQ? It's a multi-protocol messaging server. It's open source under the Mozilla public license. Polyglot in the sense that you should be able to code in Elixir or Erlang for Rabbit or any other Erlang virtual machine language, and that you can connect to it from many languages. Sometimes people ask, do you need to use Erlang to use Rabbit? No, you don't. You can use PHP, Haskell, whatever you want. And you can see which extremes I say, PHP and Haskell, right? You can go the whole spectrum of table flipping, basically. It's written in Erlang OTP, and I will show you what's good about that later. Multi-protocol, it means you can get to choose which mustache style you want. AMQP is the default protocol implemented in Rabbit. Then there is MQTT and Stomp. MQTT is a telemetry protocol for buzzword oriented programming. So if you are into the Internet of Things, MQTT was created for that by IBM, but it's an open protocol. And Stomp is a text-based protocol, which happens to be used, for example, at CERN. So if the Large Hadron Collider ever explodes, of course we won't know what happened, but it was probably because of Stomp. It's a text-based protocol, very simple. So anyway, there you can see why you may want to use one or the other. Polyglot, I said already, you can use Rabbit from Java, Node, Erlang, PHP, Ruby, .NET, Haskell, and so on. The main difference is the Java, Erlang, and .NET clients are officially supported by the Rabbit team. Then the Node client was created by a colleague that worked on Rabbit for a long time. I maintain the PHP library. Another colleague maintains the Ruby library. And the Haskell library was created by a German guy, so we know Germans commit no mistakes, so it's a perfectly working language. I say this in Germany already, so and I'm still alive. And you can use it from COBOL. And that's true, it works. And I made this joke at another conference, and the main sponsor of the conference was a COBOL shop. So they weren't so happy about this. And if people use Rabbit, yes, some people use Rabbit. Instagram, Indeed.com, Mailbox, Mercado Libre, Telefonica, like a lot of big and small shops around the world. Then you can get Rabbit from there, yeah. Of course, if you cannot download it, I should be kicked out of this. There is a simulator. You can find it there. It's the most non-responsive website you can find on the web. Because that's like, I mean, who needs responsive websites anyway? So that's a simulator, and I want to show you how Rabbit works or what's trying to solve, and then we go to the code. So the main idea in messaging is that you have a producer. The producer wants to send data to the consumer. So to send data, you need an address. In RabbitMQ or AMQP, they are called exchanges. I hope the size is fine for everybody. If I connect the producer to the exchange, and then I send data, it just dies there at the exchange. Why? Because I need to have queues. So if I instantiate a queue and bind it to the exchange and send data now, the queue goes to the message goes to the queue. And lo and behold, it queue messages. Like there is nobody connected there. If Rabbit wouldn't be queuing, like that's literally kicking me out of here. And the consumer can come later and start consuming messages. If this is too slow for whatever the reason, you can have more consumers, subscribe them to the queue, and then Rabbit will try to do the round-robin thing. Then, something that people may ask is, why do you need the exchange and why you don't just send data directly to the queues, for example? And the thing is, the exchange is just a router. And I like to give this example. If you go to the train station, I live in Switzerland. If you go to the train station in Zurich, you can buy, let's say, international or local tickets. So you are greeted by a machine. You click a button saying what you want to buy. They give you a ticket, and that ticket will put you in a queue. So you can have 2 queues, one for international and one for local ticket. And when I arrive to the train station, if I want local, I will go there. If I want international, I go to the queue, but nobody will attend me because, sorry, I'm in troll mode today. And the problem is this is my switch, context switch. I switched to troll mode. I cannot get back to talk mode. There is nobody to attend me because I'm in Switzerland. If you are in Switzerland, you want to see the wonders of Switzerland. That's why we have all these consumers or people selling you tickets. But you can also, again, come later and get your consumer and so on. So the exchange is actually implementing a routing algorithm. There are many of them. I won't go in detail now, but there is a direct, fan out, and topic by default. This is part of the AMQP specification. And they tell Rabbit how to do routing. The direct exchange is saying, select from queues where routing key equal binding key. The binding key is the one here. The routing key is the one I specify in the message. There is no SQL query because RabbitMQ doesn't use an SQL database. But just to give you an example, that's what happened with the direct exchange. The fan-out exchange just ignores routing keys. So if you need to do broadcast, you will use fan-out. And if you need to do multicast, then you use topic. In topic, you can use some patterns to decide how to route messages in a more advanced way than just what the direct exchange is doing. Questions about this? No? OK. By the way, if I'm talking too fast, just let me know. I have this Latino blood inside me that doesn't let me speak slow. So that's why you see, like, whenever you go to Latin America, you see that we are always sleeping under some palm tree because we already speak too fast. We say what we have to say, and then we have time to relax. So internals of Rabbit. Sorry. internals of Rabbit. Okay. So my idea is to give you an approximate thing of what happened in the life of a message. And of course, you have a producer, the P, will send a message to an exchange, and the message maybe gets routed to some queue, the red thing there. This is PHP code, because in a functional programming conference, who doesn't want to see some PHP? To see that we take care of everybody. In AMQP, you always need to create a connection. That will be the TCP connection, first line. Second line, I get a channel. In AMQP, you can have multiple channels per connection. That's very important when I start to explain the whole supervisor thing from Erlang. Then on the channel, I start sending commands like qdeclare to create a queue, exchange declare to declare an exchange, do the binding, then I create a message, send the message with basic publish, the message will go to an exchange. So let's say we have that code. So the question is, what happens there? I created a new connection and a new channel. I know you cannot see it. I will go in details later. But that is the supervisor tree that you will get because you started a connection, in this case, with 3 channels. If you see the structure below, it's kind of repeated. It's because in that case, that connection opened 3 channels. But more or less, that's the supervisor tree that you get out of those commands. So in Erlang, everybody knows Erlang, but let's go a bit about it for the recording. Erlang has processes. There are probably thousands of them. It's implementing the actor model, which, by the way, it's not something coming from Erlang. It's coming from later, as some speakers said today, from earlier, sorry. From Carl Hewitt and other people that they brought I think it was Planner, the language at MIT, and they tried to have the actor of formalism for it. And then, of course, from there, we have today what is Erlang. Which, by the way, the let it crash motto, let this be recorded, is part of the Erlang community. Don't try to steal it. We will fight for it. These processes will send messages to each other. Each message has a queue. Don't confuse this queue with RabbitMQ queues. Each process has its mailbox, which actually is kind of a queue where all the messages go there. And another interesting part of Erlang is that this has this virtual machine, which has a preemptive scheduler. Many languages trying to implement the actor model, but they don't have a preemptive scheduler, and everything blocks when I don't know, reading from the network or whatever. So sometimes people just say, I have the actor model somewhere in whatever language, but they forget that, and they immediately compare it to Erlang, but that's like the base Erlang. There is all this supervisor and things that we will see soon. So your app in Erlang, in this case the app is Rabbit, will be running with all this in mind. If you want to read more about how Erlang does scheduling, this is a nice blog post by Jesper. It's interesting to see how the scheduler works. Then the code structure in Erlang is very flat. You have modules. Modules will have just functions. Functions will have arity. It means that a function with the same name, let's say hello with 1 argument, is not the same as hello with 2 arguments. And of course, there are arguments to functions. And in Erlang, there is always this MFA, which is module function arguments, tuple usually or whatever. So how does Erlang look like? You have this, for example, in Rabbit, this client supervisor has a module name which needs to match the file name. It will implement a behavior, which is supervisor 2 in this case. Supervisor 2, which is today spread along way too many Erlang projects. It started in RabbitMQ, was the first project created in a supervisor 2. Then we export some functions like start link 1, start link 2, and so on. And we include some header. So that's like the basic first part of your code. And then in Erlang, you have the actual code. So you see we have 3 functions called start link, but actually, or two, sorry. The first one has only one argument. The second one has two arguments. So they are different functions. And yeah, I will explain later what that's tried to do. Supervision trees. This is taken from the Erlang docs, and that page explains a lot about how this works. You have a supervisor. It will be an Erlang process that has a special function, which is supervising other processes. It will take care that the other processes are doing what they should do. Not sure if this is politically correct to say, but will be the Stasi of your Erlang virtual machine, making sure everybody's doing whatever they have to do. Then, in the supervisor tree, you have worker process, supervisors, and you have this hierarchy of process. Which, for example, this in the client supervisor I just showed you, this is the function or the specification that's saying how to start one of these supervisor in this case. But we can have a worker, like let me just go a bit back. The one at the bottom is starting a worker, the other a supervisor. And this client knows how to start all these children. So when you have a child spec, that's something really cool for Erlang. You have the restart strategy. So by just providing this atom, you are telling what happens if your process fails. And for RabbitMQ, this is really important because we have, I will show you soon, we have a lot of processes that are reading from the network and managing the channel state. They are starting new queues, sending messages to the queues, monitoring that the queues are actually working, monitoring if the memory is not overflown and stuff like that. And they need to know what happens if one of those processes dies. In Erlang, by just saying, let's say 1 for 1, it means only restarting the failing process in that thing. This is simple 1 for 1, for example. 1 for all, if somebody fails, let's kill and restart all the siblings. Simple 1 for 1, which is the one Rabbit using in that particular module, is a simplified version of 1 for 1, which actually you can add all the children dynamically. And in the case of Rabbit, whenever you have a new connection, you have a new TCP thingy, new channel, and so on. So all these children need to be started dynamically. Then there is the max restart that the process allows in that amount of time. So you can say in this amount of seconds, you can restart this process this many times. If you keep restarting it, just bring down the app or whatever the strategy is. And this is important, for example, if you have an app that is trying to write to the file system, let's say, and the file system is full, then what's the point of keep restarting this file writer when it will keep failing? After some time, let's abort. Then the child spec has these types for the type crazy people of the other side of functional programming. Like the child spec, we have like an ID, which is just a term. You pass a start function, which is a module function and some arguments. You can tell them how to restart, permanent, transient, temporary, and so on.
Sorry.
Yeah.
Aside, was it the dialyzer's type specification or something like that?
It looks like this, yes, when you do it. If you want later, I can show you the parts Rabbit used specs. But in the docs of Erlang, it's full of this kind of stuff, telling you what each function expects to have or what they will return and so on. So it's not really enforced in the type system, but I think it's quite easy to reason about what the function is doing. So the Rabbit client supervisor, going back there, will be a simple 1 for 1. There can be no restarts. The client will be the ID, I think, module function argument, what needs to be started. Temporary is how the restart strategy works. Infinity, I think, is the time that the supervisor lets the child wait till it's killed, something like that. And this one will be a supervisor. And the M on the list at the end is for when you have a release in Erlang, we don't go there. I don't want to give you details that maybe now are not really interesting for the discussion. So a permanent child needs to always be restarted. Temporary will never be. Transient one only restarted if it was terminated abnormally. So by just having these tuples and these combinations, you have a declarative way of saying how your code should behave. There are no ifs, not case if this fail and throw this exception or that exception, do this, do that. There is not even code saying how, like, new child or new supervisor, new worker. No, you just give the spec all these arguments, and that's it. Erlang takes care of it. Which I think for a project like Rabbit, it means that there is less code being written, basically. So, and it's quite easy to go later to the code and reason and try to understand what's going on. Then we have all these words that I don't know, I don't watch Games of Thrones, but I know that a lot of people die in Game of Thrones that people like because of it, maybe, I don't know. But Erlang was killing everybody way before it was cool, basically. So Robert knows there, right? Brutal kill was there since ever. And if a child gets this brutal kill message, bye. You don't have time to collect your things. Go to talk to St. Peter as you are, basically. Timeout in seconds. Will wait this timeout before terminating all the children, and the infinity will give enough time to shut down the whole supervisor tree. So this is, in Rabbit, this is interesting. I will show you later also, because, for example, in AMQP, you can declare queues to be auto-delete, right? So the queues are deleted once you close the connection, if I'm not mistaken. So Rabbit has a process that is just tracking queue names that this connection declared. When the supervisor tree shuts down, that process will also be shut down in that specific order. So the process knows that because it's being shut down, it needs to start deleting all the queues that was tracking. So also by just having this tree of supervision, we can really know when we do some kind of garbage cleaning in the project that we have. So going back to the connection supervision tree, at the top I will go part by part. Rabbit has always this Rabbit TCP client supervisor. Whenever there is a new connection, it will start a Rabbit connection supervisor. The RabbitMQ collector is the one this side, is the one I was telling you that is keeping track of the queue names. And the Rabbit reader. The reader is the one reading from the network. And the intermediate supervisor, this one is there to keep this tree structure to know that when this thing is closed, the queue collector is closed at the same time. It's kind of hackish, but it's a way to keep the structure at the same level of the tree. So the intermediate supervisor will supervise the channel supervisor, like what is going on here, like why you have that. I told you that there could be many channels per connection, and that one channel dies doesn't mean you have to kill all the channels. So we have a supervisors of supervisors there, and then we can have the structure at the bottom replicated according to how many channels you have. So for that particular channel that you just opened, we have a writer, which will be the process writing back messages to the network. And we have a limiter, which is kind of doing flow control. So those are the end of the tree. But this supervisor will be just taking care of that part. If you open a new channel, this structure will replicate in another part. Like that. So if you open a new channel, you get a new limiter for that channel, a new writer, and so on. So for example, in AMQP, if you send a NAC for the wrong message, the specification says that you need to kill that channel. But only that channel, not the connection. So with this structure, we can kill one branch of the tree and let the other running. And depending on the message depending on the exit status of the process, the supervisor on top knows if it has to restart it, if it doesn't have to restart it, take care of it, log it, whatever. So depending on the kind of error is how this propagates up and down the supervision tree. And back to the first image, we have this is the whole structure, one connection, 3 channels. Don't know what's next. Yeah, you have a question about this? Yes? I don't know the details, but it's in our docs on the source code, explaining the reason. I know it's related to the queue collector, or when they kill it, what happened with the queue collector, but I cannot give you the exact answer. So again, I know you cannot see it, but what happens when a message is published to Rabbit? It's not good, sorry. So maybe if I do this. So when you send a message to Rabbit, I cannot see it anyway, sorry. When you send a message to Rabbit, it will call, for example, the method basic publish, and this method will create a resource with some virtual host. So, what? It will create a resource knowing in which virtual host you publish the message and so on. Then, based on that record in Erlang, it will start going through the, if I do this, maybe, wait. Never do this when you're doing a live talk, so. Whatever. So this message will start going through the Rabbit permission system, and you need to see if, for example, the user has access to the exchange where they send the message. If it has access to that particular exchange, then it will check if the exchange is actually there. It is there. It will check if the exchange is an internal exchange, for example. If it's not, you get access refused. Otherwise, you keep going that message inside Rabbit. So the process will decode the content of the message. For example, you can pass in the message some properties saying like expiration of the message. You need to decode that and see if the expiration are correct. You can pass a user ID in the message. It will say, see if that user ID is correct and so on. So this is why I told you today when we were having lunch that to those guys that Erlang Pattern Matching is better than F#. And Haskell and Clojure and bring your functional programming languages that are all worse than this. Now, except Clojure, the other one. So what's happening here? Robert, what are these semicolons there? So here we are trying to see if the user that claims to be some user is actually that particular user. So the check user ID function will get 2 arguments. One are the properties like the envelope of the message, and the second one is the channel state. This P basic is the record with the properties of the message. So if the user ID is undefined, we don't care what the channel state is. That's what we have the underscore. We just return OK. You didn't set any user ID. There is no need to validate that. Next header of the function. You set a user ID, which is then set in the variable username. And in the second line of that header, we check what username the channel has. And that's the power of Erlang. Or something that the Erlang Pattern Matching has that most languages don't have it, is the first time username is used, it will get the value, whatever that value was. The second time, because the variable is already bound, the value has to match. If it doesn't match, this part won't be executed. So by just having this part on the header of the function, you know that it won't be called if the username doesn't match. The third header of the function, the user claimed to be whoever, and in the channel is somebody else, maybe. So, okay, is that somebody else? In Rabbit, you can be an impersonator. You can tell by configuration that user can impersonate other users. So if the user is an impersonator, we return true, false, precondition failed, some error, blah, blah, blah. But by doing this pattern matching from Erlang, it's quite easy to see what's going on, and it's very short in the code, the first two cases that we want to discard. One is that the user ID was not set. Second, make sure the user ID is exactly whatever username the user provided when it created the connection. If that's not the case, then we check in the third part of the code. I told this once to a room full of Prolog programmers. They say, like, we have that every day in Prolog. But in other languages, it's not that common to have these variable bindings. So you can see what this is there. There is a blog post. Next. Then we check if the channel is in transaction mode or not. And if it's in transaction mode, we need to see a sequence for the transaction. If it's not, then we keep the flow. I won't go in detail here. Once the message passes all this part, we will create a delivery. And something that is important is this. The message got all the checks from the Rabbit logic to see if the user can publish this message, if the exchange exists, if the exchange is actually readable, blah, blah, blah. But the important part is we get a list of queue names for Rabbit exchange route. So there, the exchange logic will take place, and we return a list of queue names to see where the message has to actually be sent. And in that case, the message will be delivered to the queue, maybe one, maybe many queues. And in the case of Rabbit, we don't duplicate message content. We keep track of an index and know where the message is to prevent duplicating data in memory and on the hard disk. Then the queues, they have some optimizations, like they will check if, for example, the current, there is a consumer bound to this queue, the consumer has no work to do, the consumer told Rabbit, I don't want to hack any message, so just send them and forget them. So if Rabbit detects that case, it will just send the message right away to the user, to the connection, and won't be doing persistency at the queue level, because there is no point on doing that. So that's an optimization thing, for example. Then it will see if the message has some expiration header. If it's set and that header happens to be 0 or whatever, the message will be gone. Why do I need that? Let's say you want to say, I don't want to queue any message. If there is a consumer ready, the message has to go to the consumer. If there is no consumer ready, we don't queue. You can say, but who wants that? That's is quite common, actually, in places that if they don't have anybody to take your order, they just don't want you there because they don't have room or whatever the reason. So Rabbit can do stuff like that, for example. So after the exchange, say to which queues it will go, the queues decide if they can send it right away to a consumer, if you need to persist it, stuff like that. So at this point, we reach the message store. The Rabbit message store was made specifically for messaging. It's not using Nisha. Repeat that after me, please. Rabbit is not using Nisha for storing messages. People keep repeating that. People that do analysis on Rabbit, they say that. That's not true. Rabbit is not using Nisha for message storage. This message store will try to keep messages in memory and flash to disk if it has to. Of course, the boundary of the message store is the disk size. And there are two. There is a transient one for messages that are transient and one for persistent messages. And each queue has an index. The message is written to disk when you have delivery mode 2, which means persistent message, or when you have memory pressure. So it will start paging to disk, trying to get rid of message and free up memory. But the idea for Rabbit is to always try to send messages from memory, so it doesn't have to touch the hard drive. Why we need a custom message store? All the things is written in that blog post. If you want to see how the compaction of files is done, that comment, we have a long essay on that Erlang module explaining in detail how messages are moved from one file in the hard drive to the next one and so on. And how it reacts to memory pressure is explained there. Credit flow, I won't go too much in detail because there is not so much time, but the idea of credit flow is to prevent processes from killing each other by sending too many messages into their mailbox. That can happen. So a message, we have a credit spec saying, you can send me up to 200 messages, and after I act 50, you can send me more messages, basically. That's inside Rabbit. That's not the AMQP messages. These are Erlang messages. So I don't know if you can see it, but a process starts sending messages to another one, and the 199 messages go in 198 and so on. At some point that reaches 0, that message will be blocked. That process, blocked by the other. The other process won't let it send more messages. When does this happen? Rabbit, for example, needs to write to the hard drive. If the process that is writing to the hard drive is not fast enough, at some point it will start blocking the other processes and so on. Yeah.
Is it called backpressure?
Yes, but no. I mean, it's a credit process, and yeah, it will try to do that to the other processes, what you say, but we prefer to reserve that 10 for the network side.
But others just call it backpressure.
Yes. The thing is, when you need to maintain Rabbit and you need to reply to questions on the mailing list and you have tons of users going to the mailing list, you need to set a very specific vocabulary for whatever you are talking about, or people will start mixing things up. So we need to keep things in certain ways. Anyway, basically, a process can block another one, and then you can have a chain of blocked processes that are waiting for something. For example, the channel may be blocked by the queues. The queues might be blocked by the process that is writing to the hard drive, and so on. When this one is finished writing to the hard drive, it starts to let the others do things. So yeah, they grant more credit, the block process, and they delay granting credit. You can read more there. Next. Behaviors. This is something that allows Rabbit to be very flexible, and it gives a lot of extension points inside Rabbit. And of course, Erlang, Erlang behaviors, this is like an interface for components. In the case of Rabbit, we define what an exchange should be, what a queue should be. We have decorators, for example. We have authentication methods, and so on. So in the case of an exchange, you have this behavior with some callbacks. You need to implement route, validate the exchange, and whatnot. But if you implement that interface, you have your own custom exchange. There are consistent hashing exchange. There are random exchanges. Recent history exchange keeps track of the last n messages. React exchange, every message going through that exchange is also logged into React, for example. And there are more. So each exchange is implementing a routing algorithm, basically. Then there is all these authentication behaviors that you can specify how you want authentication to work on Rabbit. The message store index, by default, is using ETS and DETS. You can use Bitcask, LevelDB, and so on, depending on your needs. Backing queue, you don't like how Rabbit store messages to disk. You can write your own backing queue and implement a behavior. You tell Rabbit, instead of using the default, use this one. For example, in the config, you can say the authentication backends are those, HTTP and the default one. There are all these behaviors. inside Rabbit. Maybe now we have more, I don't know. And you can plug your code there. How you plug it? These boot steps in Rabbit that they build like a direct graph of dependencies. Like this bootstep will add the exchange type direct into Rabbit and requires that the Rabbit registry is already running, and it will enable kernel ready. So Rabbit will try to build a graph like this one. If you can see it on GitHub, of course you cannot see much there, but it's a graph of all the processes that start running in Erlang, and this is very declarative. It's just using the Erlang module attribute. It will run through your modules, find attributes, build the graph. If the graph doesn't have cycles, it means Rabbit can boot, for example. The federation plugin, for example, uses that for replication. You can read more about that there. I explained how Rabbit makes sure that we are using the right behavior, that we don't execute arbitrary code with those behaviors and so on. And the boot system is also explained there. And to finish, what Rabbit is doing is trying to use many of these features from Erlang. For example, the whole supervision things. Of course, it's also extended inside Rabbit with new supervisors like Supervisor 2 and stuff like that. And it's very extensible. From my experience, the thing that you can just hook by using the boot system, for example, it just lets you declare your module, add a boot step, and your module will be part of Rabbit without Rabbit even knowing that this thing is there, kind of. So we recently moved to GitHub. You can get the code there to let you know. When Rabbit started as a project, GitHub wasn't even a thing, so that's why we recently moved to it. So I don't know if there are questions. So the question is why we need Supervisor 2, why not to use the original supervisor. I think there are new restart strategies. One of the reasons is that there are different or new ways to restart processes and see why we need to restart them.
Do we have more questions, please?
Yeah. Hi. You mentioned that you're not using Nigia for storing messages and they're stored both in memory and on disk. So why aren't you using Nigia and what are you guys using?
We're using our own custom message store. Rabbit has a module called Message Store, which is implementing the whole persistent thing and paging to disk, deciding when to page to disk and stuff like that.
Okay, so why didn't you use Nigia, which was already for this purpose?
Well, it's not made for that purpose. Nigia is a database, I mean, you probably know, from Erlang, and it's made for a different use case, mostly in-memory database for their switches. Probably Robert can correct me. The case of messaging is that you have maybe 10K messages per second going through your system, or 100K, and Rabbit needs to be able to handle that use case. And those 100 messages that went there in a second, as soon as they are probably acted by a consumer, those messages are gone from the database. A normal database is usually used that you keep data on it for a long time, and then you query that data. In the case of Rabbit, no, we need to just persist messages, which will maybe be 1 millisecond inside the server and then gone. So that's the use case, and that's explained in that blog post I mentioned before. The whys of, and many people will say, why can't we just use, let's say, MySQL? Yeah, you could probably write a MySQL wrapper and put it there, but you need, in every data structure, every database has a trade-off. Maybe some have very fast writes, the slow reads, whatever. If that accommodates your use case, be happy to use, or feel free to use whatever. That's why we have a plugin system that you can put your own.
You said when the messages arrive to the queue, and if there is already a consumer connected there and there is no work for this consumer, you just send it directly to the consumer.
Yeah.
Do you actually check the size of the queue before you do that? Or you just go directly to the consumer? I mean, are you fair queue implementation, or you can just starve everything in the queue because the consumer is now free and you can just...
So Rabbit is not really doing round robin. It's like 100%. It's not here in the talk, but there is something called basic quality of service that you can tell Rabbit that this particular consumer can have a buffer of 1,000 messages, let's say, or 500 or whatever. So Rabbit will always try to fill that buffer, and then we'll go to the next consumer. And in that particular case that I mentioned in the talk is if the consumer has no work to do and is in no ACK mode. So if you're in no ACK mode, it means I send you the message and I forget about it. So because those conditions are met, then Rabbit does the optimization because there is no point in persisting the message. Otherwise, it will try to go through the normal flow of persistency or whatever.
Thanks. And last question is, how do you handle a failure, this failure on the queue side? Like if my disk dies and everything is persistent on the disk, everything goes with it?
I don't understand the question.
So I send 1,000 messages to the queue, and the queue persists them on the disk, and the node dies. What happens to the 1,000 messages that I send there?
So if the messages are there, if you can restart the node, of course, they will still be there. There is a recovery mechanism when Rabbit restart that tries to read all the things and recreate the queues.
But you don't have any replication?
There is replication.
Okay.
Rabbit has mirror queues for cluster replication, federation, and shovel for inter-cluster replication. So if you have your own local cluster, you use the mirror queues, it's called. There is a master, there will be slaves, they need to synchronize ACKs, writes, all this stuff, because one idea of AMQP is to not self-duplicated messages, so Rabbit needs to prevent doing that. Or if you ACK a message in a node, Rabbit needs to prevent that this message is sent to another consumer, for example. So there are a lot of things that the protocol imposes in Rabbit, and this replication mechanism has to take into account.
Okay, do we have any more questions? Any comments on columns in Erlang? No? Okay, thank you very much. Thanks to our speaker.
Thanks.
And now let's have a 10-minute break before the next talk. Thank you.